Today we're going to be talking about descriptive statistics, and before we start I want to just describe what the difference is between descriptive and inferential statistics are. So descriptive statistics are really our way of organizing our data, making it so we can see what it looks like. It tells us a bit about it. And inferential statistics are where we just have a question and we're trying to decide, is there a significant difference between groups, or is there a significant amount of correlation? So inferential is where we ask questions. Descriptives is where we show our data and provide information about it. So let me give an example here. Let's say we have this study. We're looking at this population of first grade children. We do these different teaching methods, and so there's a method A and a method B. And the kids that are taught by method A, their scores are seen in this box on the left. Kids who are taught by method B scores are seen on the box on the right. So let me put a little bit of, give me my pointer here. So these scores, we can kind of look at them and see if there's a difference between the groups, but it's not really that organized. It just looks like a bunch of scores. It does look from the eye that the scores on the left side are a little bit higher than maybe the scores on the right side, but I'm not even sure, it's just a quick guess of that looking at this. So the first step would be to describe our data. So in the next slide, we can see on the top that we've described our data by making a histogram. So on this side, we see our distribution of scores. Each score is represented by a box. They're stacked up on top of each other. And then we see the second sample, sample B, here on the right. So in this histogram, we can kind of see maybe there's a difference. If we start to create descriptive statistics like the mean or the average, we can see the average score is higher, 76, for sample A versus sample B, 71. So we can start to describe our data, and then the next step would be doing a t-test for this type of data, where we would have a question: are the groups different? Are the teaching methods different from each other? So in the next step would be the inferential statistics. So we're going to focus on this step 2 in this diagram here. That's the descriptive statistics, where we're trying to describe our data. So I want to go over a few other research topics before I get into how to do descriptive statistics. So just kind of a reminder of some of the things we learned in research methods. So one of the things that we learned is the independent variable and the dependent variable. The independent variable is what we manipulate. So that's what we're changing in our study. It could also be something that we're not necessarily changing, but just something that happens in the environment, and we're trying to see if that predicts the outcome. And the outcome is our dependent variable. So our dependent variable is just what happens. It's the outcome. It's the effect of the independent variable. So our dependent variable is what's out there in the environment that's caused by our independent variable. So one of the things that I do when I read research studies, I just look at tables and figures, and I can usually figure out what the independent variable and dependent variable is just by looking at the results section and those tables and figures. So let me give a few examples here. So on this slide here, what would you say is the independent variable and what is the dependent variable? So we've got two variables here. We've got wake-up time and academic performance, and then we have, this is a scatter plot that we would describe our data with. We see here some points of the data where one person's wake-up time and their actual academic performance, and based on this scatter plot, we would say that the earlier people wake up, the better their academic performance. So this is just made-up data, but in this, our independent variable is our wake-up time, and so, pardon my handwriting with this, with the mouse, and then our dependent variable, our outcome, is academic performance. And often when we see scatter plots, it's a convention to draw it this way, where the independent variable is on the x-axis, the dependent variable is on the y-axis. All right, what about this table? We've got two variables. We've got breakfast versus no breakfast, and then we have another variable, some type of scoring, which is their scores are listed below. What would be the independent variable? What's the dependent variable? This is also something that I look at when I read results sections. When I see a table like this, I see two conditions, and when I see conditions, that's usually our independent variable. So that's what we're manipulating, or maybe that's what just happens in the environment, is people eat breakfast or they don't, and then we can look at their scores on an academic performance measure. So these are their scores. So the outcome are their scores, or their dependent variable are their scores, and then the independent variable, or the cause, is eating breakfast or not. All right, here's just another example, and again we see two conditions, so this one is pretty similar to the last one, a 70-degree room versus a 90-degree room. We have two conditions, and then we see memory scores. How does temperature affect memory? So again, the outcome is memory, and temperature is affecting it. So temperature is the independent variable, memory is the dependent variable. Just some other things that we need to note when we're looking at descriptive statistics is whether it's a discrete variable or a continuous variable. A discrete variable is something that's in groups, or we sometimes call it a categorical variable. And then a continuous variable is anything that can take on any value. So reaction time is a continuous variable. So anytime we're seeing natural groups or something that we've randomly assigned to groups, that's often our independent variable, but it's often, it's considered a discrete variable. And then the continuous variable is our outcome. We'll get some statistics later on where we have a outcome that is discrete, but for now we can kind of just think of it as our outcome is usually continuous, and when we when we do an experiment, we have our independent variable as categorical or discrete. That's kind of an easy way to think about it. There will be exceptions as we get into more complex statistics. All right, so one of the things that we'll do when we describe our data is to put it in a frequency distribution. And so what we have here on the right-hand side are some scores. And then, so this column here are the scores, so that people can score 1, 2, 3, 4, 5. This is, again, not very creative, made-up data. And then on this column here is the frequency. So 2 people had a score of 5, 3 people had a score of 4, 4 people had a score of 3, etc. So we can graph this data, and basically it's like what I showed you earlier. We put boxes, each score represents a box, and so we have one person who scored a score of 1. So here are the scores on the x-axis. So the score is 1, 2, 3, 4, 5. And we have the frequency on the y-axis. So one person scored a score of 1. We have 2 people, and if I actually drew these as boxes, we'd have 2 boxes. So 1, 2 people, the frequency of 2 scored a score of 2. For the score of 3, we have 1, 2, 3, 4. So 4 people scored a score of 3. And then we have 3 people who scored a score of 4 and 2 people who scored a score of 5. So the frequency distribution gives us an idea of what our sample looks like, and it makes it much easier for us just to look at our data. We can see most people on this exam scored a score of 3. So it's the highest number of boxes. It's where the most people scored. And then we see the fewest people at sort of the extremes. And if we think about this, this is pretty much what a normal curve looks like. So when we graph our scores in this way, we can see that normal curve. We can see where the middle is, and then where we can see the extremes are. We won't always have a normal distribution, but in this situation, we do. When we have discrete or categorical variable, we tend to just make a space between the scores because it's not a continuous measure. We would just want to show it's not continuous. So with the frequency distribution, they're pushed together. And then with categorical data, we just put it in a bar graph. It's basically the same thing, but we just put a space between them. So personality types, we don't think of it as a continuum. They're actually categories. So personality type, type A person, type B person, type C person. These are categorical, so we put that little space in there. All right, so one of the things that can happen is if we change the y-axis, we can really change the way our data looks. And so if we look at these two figures, it's charting the exact same data. It's the number of major felonies for this time period from 2003 to 2005. And we look at it, 2003, there's about 219 felonies, 2004, 225 felonies, and 2005 it gets a little bit higher. So on this graph on the left, our range goes from about 210 to 235 or so. On the figure on the right, we have a much bigger range from 0 to 800, and we can't see the jump in the felonies as much as we do on the figure on the left. So this is one of the things that is often manipulated, manipulated is a strong word, but is often changed to kind of show more or less of an effect. So if we look at the figure on the left, we can say, oh wow, felonies are really going up every year. We look at the figure on the right, we say, well, felonies are pretty flat. So changing that y-axis can really make our data look more significant or not. So one of the things that I see when we run our statistical software is the software will decide what the axis is, and it will actually often look like the one on the left. The software is trying to make the range fit the data, and so we see changes that sometimes aren't significant. So that's something just to pay attention to. What is the range of your figures you're creating? So another thing that we'll look at is the symmetry of our distribution. So when we do that frequency distribution or the histogram, we want to see, do we have a normal distribution? So this normal distribution up here on the left, so it's symmetrical, where we have the most people in the middle, and that's the highest frequency, the lowest frequencies in the tails. We could have what's called a bimodal distribution. So this is the figure right here to the right of that. So we have two modes. So basically we have 2 points where we have the most people. So that's a bimodal distribution. And I'll go through another example later on in the slides where I demonstrate a bimodal distribution. And then we have a positive skew and a negative skew on the bottom. So the positively skewed distribution is where the tail of the distribution goes in the positive direction. So that's how I remember it. It's in the positive, more positive direction. That's where this little part of the tail is. And a negative skew is where the tail is going more towards the negative direction. So one of the things with a positively skewed distribution, an example might be income. So if we look on average, most people's income is right here. So that's the average income. But if we have a few outliers, we have people who have a great deal of money. Elon Musk or Jeff Bezos or Oprah Winfrey, they have a great deal of income, but there's not many people with that much income. So that's a positively skewed distribution. And so we'll talk about ways we can look at positively skewed distribution so that we don't have that skewed look at it. And then a negatively skewed distribution is often something like grades. So quite often most people are getting pretty high grades, right about 85 to 100, and then we have a few, once in a while you have just a bad grade, and that's a negatively skewed distribution. So just a few people with really poor grades, let's say. So theoretically that's what that could look like. All right, so let's get into the topic of central tendency and variability. And so we were able to graph the data with some of these figures that I showed, and we'll show that in the statistical software at some point in time. But now let's talk about some numbers we can use to show a central point and how wide that variation is. So one of the things we can do is find one number to describe our data. So there's a few things that we'll use to describe our data this way. The first is the mean, and I think everybody knows what the mean is. It's the average. Here in this slide I have the average formula drawn out. It makes it look much more complicated than it is, but this Greek capital letter sigma usually describes the sum. So we're going to sum up all of the scores, all of the x scores, and then divide by n, or the number of scores. So we just add up everything and then divide by how many people we have or how many scores we have. So let me give an example of this. So what's the mean of this set of scores? So we've got 2, 2, 6, and 10. If I add these up, I get 4, 10, 20. So 20 on the top. And again, I'm drawing with the mouse. And then we have 4 scores. So our sum is 20. We add up the scores, we get 20, and we have 4 scores. So the average score, 20 divided by 4, equals 5. So that's our middle point. If we wanted to know what the average score is, that's our middle point of 5. Let me do this in a different way. Let me show it on a seesaw. And I like the seesaw example because it will help us in a few minutes when we look at outliers. So I have the same scores. I have a 2, a 6, and a 10. We already calculated the mean in the slide before, and we know the mean is at 5. So the mean here, this Greek letter mu often describes the mean, the population mean when we're using Greek letters. So this 5 balances all of the scores. So we can think of the mean on a seesaw as balancing all the scores. And I'm going to come back to that in just a second and why that's important. But this 5 balances all the scores. All right, so what's the mean of this set of scores? 3, 6, 6, 9, and 11. If we add those scores up, we get 20, 26, 32, 35. And we have 5 scores. So we get a mean of 35 divided by 5 equals 7. I hope that's right. Yep, it's so our scores, we add these up, we get 35 divided by 5, so our mean is 7. We put it on this teeter-totter or seesaw, and our mean balances the scores at 7. So a theoretical question: what happens if in our set of scores we get one more score and the person's 85? And this is almost as if we're calculating everybody's income, and then in walks somebody in the room that makes a ton of money. So this person scores 85. What happens to our mean? And we can think about it. If I could keep drawing, I'd have to draw a long ways, and then eventually there'd be a box for the 85. So we can think of our seesaw as having to move a great distance to balance out this new score. So when we have an extreme value, our mean gets pulled towards that extreme value. Let me just show that. Here's the actual calculation of that mean. So when we now have this, previously our mean was 7 with just the first 5 scores. We had that 85 in there. Now our mean got pulled all the way to 20. So when we have extreme score, so I'll draw it here, this one extreme score of 85, and before all of our scores were way over here. I'm not going to draw them very well, but our mean got pulled this way to balance this one extreme score of 85. So our mean is not necessarily the best measure of the middle when we have extreme scores. So when we talk about home prices, if you talk about home prices, I don't know if anybody talks about home prices, but we don't talk about a mean home price because there are some really expensive homes that throw that mean off. We actually will talk about the median home price, and I'll show the median in a second, but that's because the mean is pulling that, or I'm sorry, the mean is pulled by those extremes. So we don't talk about mean income either, because that would be pulled towards extreme scores. So we have a positively skewed distribution. The mean gets pulled towards those extremely high scores. So let's see if we can kind of play around with this a little bit. We have a sample with a mean of 30. If one score with a value of 10 is removed from the sample, what effect will it have on the sample mean? So we don't have all the scores. We can't actually calculate this, but let's think about it theoretically, what happens. And let me just create some scores to make it happen. So let's say we have a 10, a 30, and a 50. Oops. Our mean is currently balanced at the 30. If we remove the 10, the mean has to increase to balance the higher scores. So our sample mean will increase. So we remove a low score, our sample mean increases. So one way to think about this is if we have quiz scores, if I drop the lowest quiz score, the mean increases. If you've got all of these really high quiz scores, but you did one that's really poorly, I drop that score, the average of your quizzes goes up. Let's give another example. A sample of 40 scores. It doesn't really matter how many scores we have. That's kind of meaningless information in this question. Has a mean of 75. If one new score with a value of 90 is added, what happens to our sample mean? And again, I'm just going to give the example of quizzes. Let's say your average quiz score right now is 75, and you get a 90 on the next quiz. What happens to your quiz scores, or average of your quiz scores? It goes up. So we add a higher score than the mean, our mean will go up. If we remove a lower score from the mean, our mean goes up. Okay, I'll skip over that one. So our mean, again, has a bit of a problem. It gets pulled by extreme scores. So we're going to need to find a way to quantify our middle number if we can't use the mean, if we have extreme scores. And one of the ways I've already mentioned is to use the median, and the median is simply the middle number. So if we have an odd number of scores, it's easy just to find the middle number, and that's our median. If we have an even number of scores, we have to find the middle two numbers and just take the average of those middle two numbers. So let me give you some examples. What is the median of this set of scores? 1, 4, 5, 10, and 50. Again, if we tried to calculate the mean, that 50 would really pull that mean quite a ways, but the median is just a middle score, so it is 5. And then in this example, a little further down, we have the numbers 3, 3, 4, 5, 7, 8. We don't have a middle number. We have a middle two numbers. So the median is 4.5. So in this example, again, the median is 4.5. What if we took that last number and it's not 8, it's 800? I really have to draw better than this. So the last number is now 800. What happens to our median? Absolutely nothing. Our median stays exactly 4.5. It doesn't get pulled towards those extreme scores. The mean would get pulled quite a bit, but the median is just the middle number. So here's an example of this with the four numbers drawn out. What is the median of this set of numbers? The median is 8. We have a middle number of so 3, 5, 8, 10, 11. We have a middle number, so the median is 8. When we have this set of numbers, what's the median? 3, 3, 4, 5, 7, 8. We don't have a middle number by itself, but we have these middle two numbers, so the median is 4.5. So here's another example. Let's say we have this set of numbers, 2, 2, 2, 3, 3, 12. The mean is 4. So if we calculate the mean is 4, but our median stays right here at 2.5. So our median doesn't get pulled towards that extreme value as much. All right, what's the median of this set of scores? 1, 3, 3, 5, 6, 7, 8, 23. And the way that I do this is sometimes I just cross out numbers, if you can actually cross them out. So I'll just cross out until I get to the middle. And I've got a middle of 5 and 6. So my median is 5.5. Okay, so the median is actually a pretty good number. It tells us a lot about our data. Maybe another number that we might have another measure of the middle, and that's the mode. And this is the number that's the most frequent. So in this example here, 3, 3, 4, 5, 6, 6, 6, 9, 14, 28. 6 is the number that we see most frequent, so that becomes our mode. And when we have a lot of numbers, our mode can be pretty useful. It tells us what number showed up most often. I work with a lot of people with OCD, so that's why I use 666. It's just to kind of push the boundaries a little bit of their OCD. So, but in this example here, we have the mode is 666. So one of the unique features of the mode is that you can have more than one mode. So in this example here, we've got the number of fish caught, and early morning, there's a pretty high frequency, and early evening, there's a high frequency. So at 6 a.m. and 6 p.m. is the time where most fish are caught. We can say this is a bimodal distribution. And again, we'll see this with the two peaks in that frequency distribution histogram. All right, so in an ideal situation, when we have a perfectly symmetrical distribution, the mean, the median, and the mode will all be that same number. So the mode is the number that's most frequent. It'll be the highest number in our frequency distribution. The median will be the middle number. And then the mean is calculated as the average of the numbers. And they'll all be equal in a perfectly symmetrical distribution. And this is just a question of kind of just that same knowledge. Perfectly symmetrical distribution, a mean of 30, the median would be exactly 30. So if it's perfectly symmetrical, we know all those numbers are equal to each other. When we have a positively skewed distribution, we showed this with the mean examples, we have the mean gets pulled towards that tail. So again, if we have somebody with a high income, the mean gets pulled the most. The median will get pulled a little bit, and then the mode stays the most frequent. So the mean is pulled the absolute most towards extreme values. Same thing with a negatively skewed distribution, is just pulled in the opposite direction. The mean gets pulled the most towards those extreme values. So again, if you have a low test score, the mean gets pulled towards the lowest end of things. All right, so if a distribution is positively skewed, what's the most probable order for these three measures of central tendency? And I'm going to draw this out. So I need to think of what a positively skewed distribution looks like. So I'm going to just draw this out, not very well, but so here's my semi-positively skewed distribution. We know the mode will stay in the middle. The mean is getting pulled the most towards that tail, and then the median is going to be pulled the second. So if I know the numbers have to be 40, 50, 60, this is going to be the lowest number. 40 is the mode, 50 is the median, and 60 is the mean. So let me see if we here, It looks like B is the correct answer. 60 the mean, 50 the median, and the mode at 40. So the mean gets pulled most towards the positive direction. All right, so with the mean, the median, the mode, we have a measure of the middle, of central tendency. We don't know how wide the distribution is spread. So we need to get another measure of spread in the distribution, or variability in the distribution. So we're going to look at ways we can look at variability now too, to get that other piece of our distribution. So we've got a couple of ways we could look at this. One is range, and just the range is simply how wide our distribution spreads. So we can calculate the range by taking the highest number and subtracting the lowest number. So if we look at these numbers here, 3, 6, 9, 11, 13, 20, the range is 20 minus 3, or the range would be 17. So range tells us a good amount about our distribution. It's a pretty good number. It's easy to calculate. The problem with the range is it gets pulled towards extreme values. So again, if we have a 200, now all of a sudden our range is a lot bigger because of just one number. So it doesn't describe how everybody fits into that variability. It just describes, one extreme value almost. So the range won't be a perfect number, but it's a pretty good estimate of variability. We can also do an interquartile range. So if we split up our distribution into quarters, the interquartile, we took the first quartile and the third quartile and just looked at the range in between those. So if we kind of split this distribution up into quarters, we're going to do it mathematically. I'm just kind of breaking it up like this. We could look at the range between 6 and 13. That's not the right way to calculate interquartile range, but I'm just doing it roughly. So it doesn't get pulled towards those extreme values as much. So interquartile range is a bit of an improvement. I'm not even going to go into how to calculate it. Use statistical software to calculate it. I don't think it's worth your time trying to calculate that by hand. I think software will do it if you even want to use it. We're going to go over some better measures of variability in a second. All right, so another idea is if we could look at how far away each number is away from the mean. So how far away each number deviates from the middle. And that we might call it a deviation score. So if we looked at how far away our number deviates from the mean or the middle, we could then look at a bunch of deviation scores and take an average of those deviation scores. So how far away on average is each score away from the middle? That sounds like a really good idea, an average deviation from the middle. The problem is whenever we calculate that, we always get 0. Let me just show you why kind of briefly. This is not all that important, but let's say we have this set of numbers, 3, 4, 7, and 10. So 3, 4, 7, and 10. We take the average of that, and it's 6. So if we take away the score from the average, so this is 3 less than the average. The 4 is 2 less than the average, 7 is 1 more than the average, and 10 is 4 more than the average. We add these up, these deviation scores, and we end up with 0. And that's always the case because the mean is, mathematically, the mean is in the middle. If we average the deviations from that mean, it's always going to equal 0. So that's a great idea, but it just doesn't work mathematically. So we have to do something else. And this is where it gets way too complicated, but I want you to know what's happening behind the scenes when you see this number. I'm not going to ask you to calculate these by hand, but just so you can see what's happening. So let's say these deviations from the mean were a good idea. Let's say we square these deviations. So again, we have 3 is 3 units away from the mean. It's minus 3 units away, 3 less than the mean. We take this negative 3, we square it, and we get 9. So minus 3 times minus 3 is 9. 4 is 2 less than the mean, which is 6. And we square that minus 2, we get 4. 7 is 1 more than the mean. We square 1. 1 times 1 is 1. 10 is 4 above the mean, so 4 squared gives us 16. We can add these up and get 30. And then if we take the average of those 4 numbers, 30 divided by 4, we get a nice number. We can divide that by the number of scores. 30 divided by 4 is 7.25. I don't know, and top of my head. But we get a variation number. So we can do this 7.5. It's on the next slide. Always wait to the next slide. Don't try to calculate in my head. It's probably a good rule for me to follow. But anyways, so 30 divided by 4 scores gives us 7.5. And we call that the variance. So the variance is a nice number. It tells us, how far away things are from the mean. But the problem is we squared everything. So the squared numbers don't really mean all that much. They're not on that same metric that we were originally on. 7.5 doesn't really seem related to this original set of numbers, 3, 4, 7, 10. So what we need to do is to unsquare that number. So what we're going to do is take the square root of 7.5. And that will give us what we call the standard deviation. So if we calculate the variance by squaring everything, we can unsquare it, take the square root of it, and then we get what's called the standard deviation. And the standard deviation is how far on average each number is away from the mean. So that's going to be a really important number. The standard deviation is that metric that tells us on average how far away a number is away from the mean. So we'll see this written as S quite often. If we see it written as S squared, that's at the variance. So that's before we do the square root of it. When we do the square root of it, we get rid of that square, and then we call it the standard deviation. So when it's got that little squared sign, it's a variance. When it doesn't have it, it's a standard deviation. When we're talking about populations, we often just use the Greek letter, so we use the lowercase sigma. And so again, there's no squared sign, so this is population standard deviation. And when we have the sigma squared, that's a population variance. So when we're working in this class, we're going to be working with samples. So we're going to be talking about S's, but sometimes you'll see that sigma when we're looking at hypothesis testing, when we're talking about the population. So we'll use the Greek letter when we're inferring to the population, but we'll use the S in practice because that's actually all we have is a sample. All right, just kind of quick reminder. We tried to find out how far away each number was away from the mean. Those are the deviation scores from the mean. If we took an average of those deviations of the mean, it didn't work because we always got to 0. So we couldn't follow that path. That would have been the easiest path. But if we square each one of those deviations from the mean, we square each number, how far away each number is from the mean, we find the average of those squared deviations, and that's the variance. Then we can take the square root of that to get to the standard deviation. So we had to follow this convoluted path to get to the standard deviation, but that number is the most meaningful for us. It's on the same metric that where we started, and it's not 0. So I hope that made sense where we get the standard deviation. If you don't remember how we got there, the standard deviation is simply the average distance away from the mean each number could be. All right. So when we put this all together, I'll do it on this slide here. I like it a little bit better. We'll get a number that describes the middle, and we're talking about population, so we're using Greek letters, but this is the mean of the distribution, and then the average distance that we would expect each number to be away from that average. So this is the standard deviation. So with two numbers, we can really describe our distribution quite well. So we have the average and then the standard deviation.